The title of the talk is Electrochemical Additive Manufacturing Challenges and Opportunities. Now I would like to invite the session chair, Professor Josh Matthew, to start the proceeding of the session.
Good evening. So this session is the talk is given by Prof. Murali Sundaram. Dr. Murali is a professor of mechanical and materials engineering at the University of Cincinnati. He had his master's and PhD degrees in mechanical engineering from IIT Madras and NTU Singapore respectively. He has over 25 years of professional experience that includes 10 years of industrial experience in precision manufacturing and 3 years of postdoctoral research experience in micro and nano manufacturing. Dr. Murali is a recipient of a Faculty Early Career Development Award from National Science Foundation. His research interests include additive manufacturing, nano manufacturing, non-traditional machining, micro machining, hybrid machining, CAD/CAM, metrology and process simulation. Dr. Sundaram is advising or co-advised about 40 graduate and hundreds undergraduate students. He has authored more than 100 reputed publications. Dr. Murali serves as an Associate Editor of SME's Journal of Manufacturing Process and is a member of ASME and SME. So I welcome you, sir. Thank you.
Thank you, Chair, for that introduction. And before I begin, I would like to thank the conference organizers for their excellent arrangements. It's one of the smoothest conferences that I am attending, and thank you for all your effort. So my topic today is going to be electrochemical additive manufacturing challenges and opportunities. The reason for choosing this is some part of it I spoke in the co-open last year in IIT Kanpur, and I received a lot of interest, a lot of questions. So I thought maybe I can add a little bit more to that in this conference. So when I told my students about this, they got super excited, and then they gave me about 120 slides, each and every damn thing about that process, and saying, okay, what will happen? Are here to think out of box, try to come up with some new ideas, give some hint on what is actually missing. I'm not going to tell how to get there, but I will give, at least you can think of it like a case study, how I am doing it. But that may not be the only way to do it. So there can be many more ways, so that way it will trigger your imagination. So you can come up with your own idea that may become your thesis. I don't know. So that is the idea of this talk. So we will start with an introduction to ECAM. If you are hearing that term for the first time, I will give a brief introduction about it. And then the multi-material deposition, that is the most challenging in ECAM. I will talk about it, what we have done, particularly in compositional grading and all. And then I move on to talk to you about the design tool. Tailored materials is the incoming thing. If anybody is actually looking for some research proposals for grants and all, this may be an excellent area for you to think about. And in tailored materials also, design tool is not there to the best of my knowledge. So I will outline one way of developing a design tool that I have done. There can be many more, and then I will end my talk with some futuristic work, particularly topology optimization. So before I go further, my apologies to organizers for this morning. I could not attend the whole session because of some health issues. I consider that kind of non-professional. Even now my voice is not getting back, so in case you are not able to hear anything, please feel free to stop me. I'll try to explain. Okay, so let us begin. What is the ECAM? ECAM stands for electrochemical additive manufacturing. The idea is combining the principles of electrode deposition with additive manufacturing. So a lot of new ideas are coming into additive manufacturing. So additive manufacturing for polymers, additive manufacturing for metals, additive manufacturing using ultrasonics. So many new ideas are coming. So this is one such concept where can we do additive manufacturing of metals at room temperature. Most common thing that you will see for metal additive manufacturing, they will use some kind of heat source, mostly laser. That brings its own thermal damages. So is there a way that we can avoid that? That is the idea. So you try to combine this localized electrochemical deposition and this concept of modeling your design, what you want to do, and then trying to make a physical object of your model, right? That is the fundamental of additive manufacturing. So are you able to do these kind of things? So what I'm showing you here are some of those examples. These are some freestanding structures. And why I show you this is the moment you say electrode deposition, people will think about planar structures. Coating, the name itself says electroplating. That is no longer true. You can have some freestanding structures like this using the principle of electrode deposition. And the key here is localization. The deposition by nature will try to spread out. It will try to make a thin films. Then over the period of time, we can make it thicker and thicker. But if we can come up with a method to localize the deposition to one point, that is the starting point for you to achieve ECAM. Here again, I will repeat what I am doing, but that is not the one and only method. I am only telling you what is the requirement. You start thinking about it. Can there be any other thing? For example, you can put a mask, you can open only one spot and then allow the deposition to happen only there, right? You can do that way also. I don't want to do that because mask will bring its own problems. I want to stay as a maskless, but still you have to control it within a small area, how you can do that. So I'll throw a few questions like that through this talk. You can see what I have done, but please don't stop there. Ask yourself, is there a better way of doing it? That way, the research itself will become better. So it's kind of similar to electroplating or electroforming. The only difference is in electroplating or electroforming, you have to have a base material. On top of it, you can do the coating or anything, but when it comes to ECAM, there is no base material at all. So it is just a CAD model. That CAD model is bringing some physical objects, so that is the key difference. So how we do that? We use that anode to move it, that where it goes, the tool path is directed by the CAD model. So wherever you need the material, the tool will go there and the deposition is going to happen. So I use micro tool because I don't want this deposition to spread out to more than the voxel size. So if you are familiar with additive manufacturing, you may be knowing this. Additive manufacturing can be done either by layer method or by voxel method, right? So I use voxel method here. So my goal is to restrict the materials within that voxel. So the basics still remains. The electrochemistry won't change whether you are doing electroplating or forming or ECAM. Still it is the redox reaction. So you have the metal ions and then you do the reduction reaction to get the solid product deposited. Lots and lots of process parameters are there. Each will play a role, and you can have plenty of studies on every aspect of it. I am not listing down everything in this fishbone diagram. Some of those things, in my opinion, that I felt the most dominant influences, only those things. For example, electrical parameters are many, but the pulse frequency, the voltage, these are playing a very big role compared to other parameters. So CAD-CAM integration, this is a fairly straightforward thing. Once you have an idea, so you need to execute it. So you have to have an integration system to do that. This is how we are doing it. So we have an in-house built deposition system that I'm showing you here. So you start with the CAD model, you visualize it, send the toolpath instructions, have some kind of control system. I will come to that in a minute. And then you try to make the part whatever you designed. So that is the whole flow. Process control, again you have two options. Either you can have open control, which basically means you will follow the Faraday's law, apply Faraday's law and hope that whatever material you theoretically you are supposed to have it there, it is there. Move on to the next one. So that is one approach, it's an open control system. Or you can have a closed control system where you can monitor the current that is in the electrochemical cell. So you can constantly monitor it. So you can visualize it. If I have my base or my previous voxel sitting here, and if I have my tool here, the gap between this tool and my base decides the voxel height, right? So as the deposition starts happening, you can see the process molecule current will keep changing, and the moment this full deposition comes and touches, current will peak, right? It's a short circuit. The idea is you don't want it to happen, but you should have a threshold value. So if it comes up to that, then you know that it is done, you will move to the next one. So this illustration probably can show you that. So if you see here, you have this deposition happening. When it comes too close to the tool, then the tool goes to the next position and then it repeats. Okay, so I will show you a demo of the ECAM to get you the concept. So let us say this is the design that we have. So basically, like I call it street lamp. You can call it in whatever way you want. So basically a post and then an arm and then a lamp hanging something. It doesn't look like a lamp, but image. Okay, so if this is the design I have, then first thing is I decide on build order in what way I'm going to build it. So obviously I will start with the vertical thing because that is what is connecting to the base. So I have to start from there. This is a fairly simple thing. So it has to follow this 1, 2, 3, right? But as it goes a little bit more complicated, there are some logic you should apply. I will come to that in a minute. But to begin with, we will take this very simple thing. Now if you watch this video, you can see those numbers there in the video that we show 1, 2, 3. That corresponding shows 1, it is building that vertical part. The moment it shows 2, it is building the horizontal part. Okay, so please follow the video like that. So now this 2, horizontal part is building, and then it will come down. Okay. You would not have seen such an additive manufacturing anywhere else. Have you ever seen an additive manufacturing where material is added from the top to the bottom? So this process can do that. So I will now go back to the presentation mode. Okay, so here there is a comparison to justify why there is a need for such a new additive manufacturing process. There are already so many additive processes, so why you need yet another? So this is a comparison. If there is any expert here in additive manufacturing, please forgive me because everyone thinks their additive manufacturing is the best, right? So I don't want to offend anybody, but this is what I felt. If you compare to material jetting or material extrusion or stereolithography or selective laser sintering, compared to that, we feel ECAM can do certain things that other process cannot do. So the color code here is red means it cannot do, yellow means it's somewhat okay, average. Same thing goes for the smiley face. Alright, so why ECAM? To begin with, ECAM can make metal parts at room temperature. Not many processes can do that. So your source material, it need not be solid alone or liquid alone like that. It can be solids, it can be liquid, it can be even powder. So wide variety of source. Again, the size, not many process. Yeah, additive manufacturing process can do additive manufacturing at all levels. So even if, for example, laser, if you can think that laser can do solid laser sintering at the macro level or micro level, you have to change the laser source and all. Other processes simply they cannot do anything. They may be able to do at the micro level, but not many processes can do at the nano level. Maybe two photon polymerization, something like that possible. But this one, by its nature itself, electrochemical manufacturing, you are adding materials atom by atoms, whether you like it or not, the process happens at the nano level. So it's up to you whether you want to go to micro or macro level. So all this can be there. And this last point that I'm saying is the real unique aspect of this. Most of the times when you talk about additive manufacturing, you'll be saying the z-axis building, right? So you will add material layer by layer in the z-axis. No such restriction here. As you saw in the earlier video, you can add in the z-axis, you can add in the x-axis, or even you can add in the negative z-axis, or it can be like 360. Anywhere you'll be able to add. So that should trigger lots of imagination in your toolpath planning if you are thinking of any research topic. None of the existing toolpath algorithms will work. That is 70 things you can think if you want to exploit that feature totally. So these are some of the ongoing studies that are going on in my lab. Obviously, I'm not going to touch upon each and every one of them. So we already have a couple of US patents and few PhD and master's thesis completed. Several other students are working on it. So rather than going into each and every aspect of it, so I'm going to focus more on the multi-material deposition because I feel that is where the real challenges are there and the real opportunities are also there. So let me touch upon the challenges. So when you have electrochemistry is a crazy animal, you have to train that for each and every metal system. So when you are bringing in what is really good for one metal may not work for another metal. So it's not like traditional process like milling, for example. Milling I can classify, I can say, okay, these materials belong to ductile material, these materials belong to brittle materials. What process parameter I am fine tuning for ductile materials, more or less they may work. So what I do for aluminum, if I try for copper, it is likely to work. Here it is not like that. So each material you have to think and come up with the right chemistry for that. That is a challenge. Then even if you are able to deposit uniformity, repeatability, microstructure, all these things are there and how quickly you can do that repeatability. There are several aspects. And right now my group is focusing more on the bath composition because we feel that will make a huge difference. For example, last year when I was talking in co-op, I was demonstrating something. Today, if I have to repeat it, I can do it 50 times faster just by changing the bath composition. That paper we are going to publish soon. I'm not going to give the details to you now, but I'm telling you the importance of bath composition. So let us touch upon multi-material deposition. So initially we started doing this multi-material thing. It's very simple. If I want to deposit more than one material, I should have more than one metal ions. That's it. So I can have some salt solution where I can put more metals in the salt solution. Then if I try, more materials should deposit, right? It's a very straightforward thing. That is what you are seeing here. So we tried nickel and copper and we got this deposition. Now, if anybody here is familiar with chemistry, electrochemistry, you will be noticing putting nickel and copper in the bath and then doing deposition of both is not a great deal. What is great deal is if you look at the composition, you will notice nickel is 80%, copper is 20%. If you go and try this, you will see it the other way because copper is easy to deposit. So it will deposit more and more compared to nickel. So how did I get this one, right? That is a research. So there has to be a way to override the natural preference, because in real life if you want to apply this, the composition is not decided by you. Composition is decided by the customer. So if the customer wants it 60-40 or 70-30 or 50-50, your system should be able to do that, right? So we did some research on that. I'll come to that in a minute. Once we were successful with 2 materials, then we tried to expand that. So what you are seeing here is a 4 material deposition. Nothing like the same idea. So have those ions, whatever you want to deposit in the form of salt solution in the bath, and do the deposition. So quickly look at this. So this is the nickel copper deposition that you are seeing. And if you want, I told you, right, copper is likely to be more, but if I want nickel to be more, what can I do? I'm not going into the DOE and all, but if you look at the things, you can see whatever the pictures here, the same thing you can see. For example, I have to increase the deposition voltage, it will give me more nickel. So frequency, I have to reduce. Certain other points I did not tell. For example, it's common sense. If I want copper more, then have more coppers and nickel more, then reduce the amount of copper salt that goes into the bath, right? That's why bath composition is very, very important. I am not touching on that aspect here. So this is for the 4 metal deposit. Here again, if you see, there are certain process parameters. They don't combine very well, they don't do a good job. So in this case, the second case, for example, if you take the combination of voltage and high frequency, the deposit that you are getting is very, very fragile. So remember earlier I was talking about localization, how you will do that. Frequency is one such a big deal. So you try to increase your pulse frequency, the deposit you are going to get will become thinner and thinner. The problem with that is if it becomes too thin, it will become very fragile. So it may break off easily. So there is an issue there. That's why I have this talk as challenges and opportunities. It is not like a freeway path. Okay, now this is fine. You can have the salt solution and do that, but if you really want to make it a commercial system, then what you need to do is you have to have a mechanism where whatever is the metal that you want to deposit, you should have it like a sacrificial electrode, like a solid form. Try to get those by dissolution and do the deposition, right? That will be straightforward rather than. Why I am saying this is if I do this earlier approach of mixing the salt solution, I cannot take it out. Right? Once I mix, it's done. How will I take the iron out? So in this case, the advantage for you is you start with a neutral bath, supply the ions, do the deposition, then stop, deactivate that particular electrode, activate whatever you want. So that is the advantage of this. So this particular setup will be having multiple anodes. So each anode will be an ion supplier. So you can pick and choose which one I want. It can be more than one also. So depending on your requirement. So the chemistry is very important. Not all ions will behave very nicely. For example, in this situation, the copper will be the rogue. Nothing can control it. You start, it will start depositing. On the other hand, if you look at molybdenum, it won't deposit by itself at all. So you have to have something to do a co-deposition. So in our case, we tried iron with the molybdenum, that became good successful thing. And even within this iron group, you can have some preference. Iron will be doing much faster than copper. Nickel is the most challenging thing. So you have to have a very good understanding of the chemistry. There are a lot of ways you can do that. You have to understand the role of each and everything. For example, if you have H2SO4, you can have the overall pH control. If you want to have the pH control only at the cathodic region, then that can be done by this H3BO3 boric acid that acts like a buffer solution. You can do that, and then you can have complex reagent. Very, very important. Very, very important. Complex reagents again is a world by itself. I'm not going to open that topic, but appropriate complex reagent for your material system is important. So once we have the concept how to implement that, we have this setup that is inbuilt. We built it in house. What you are seeing here, this electronics, this is basically a potentiometer. Okay. So why you need so many of them? Because you want to control each and every electrode individually. That is why you have such a pile up of controls. I have some videos to show you, but I don't know whether they will run. If they run, it is good. Then it runs. Okay. So this we built ourselves because we did not see any commercial multi-potential stack that can control like 16 channels or something like that. I don't know about it. If it is there, I don't know how much it is affordable. So we made this by ourselves. And once you have the system ready, then you need to have some kind of monitoring system to know how much of metal ion your source is going to supply, right? You will have a quantity, how much you need. So you have to have a system for that, and your bath composition you need to fine tune. This is what I am trying to show you here. So you start with some common bath, and then try to deposit material. If the material gets deposited, that is fine. If the material is not getting deposited, you have to have some kind of adjustment, either pH value or whatever, and that way for each of this material you should work out the chemistry so that the deposition or this dissolution can happen. So that is one requirement. And then the second requirement is, even for the right bath, if you are going to do the dissolution, how much of iron has gone into the bath, how will you know? This is the good thing with using the salt solution, right? If you have the salt solution, it is very, very easy for you to prepare the electrolyte with whatever molar concentration that you want. Your basic chemistry will tell you that. But if you are following this approach, then you have to have a mechanism that will tell you, okay, this is the amount of iron that will go into it. So this is the logic that we used here. Basically, it follows Faraday's law. Alright, so we use this particular system to do this dissolution and deposition. For some reason I am not able to see. So what you are basically seeing there is your feedback signal that you can monitor that you are seeing on the right side, and this side you are seeing the color change. If you look at it carefully, for my eyes I am not seeing anything. You have a good eyesight. You should be able to see the liquid changing the color. That means the ions are getting dissolved in it. You can just skip this. Okay, so this is the basic idea of multi-material. Okay, so you can use the ECAM concept, you can use multi-materials, especially if you can have sacrificial electrodes, then you have the freedom to choose what will be the different element, what will be the composition, and all those kind of things. Okay. Now, having understood this possibility of multi-material deposition, whatever material you want, if we can combine this with careful toolpath planning, that opens up a lot of new opportunities, particularly in graded materials and tailored materials. So before we move on to that, I just touch upon very quickly what is the toolpath planning that we are doing. There are many things we can demonstrate. I am going to demonstrate only one aspect of it. If you remember earlier that street lamp post example I showed you, if you do it with the normal, for example, powder bed additive manufacturing or any other additive manufacturing, how they will do is the vertical thing, no problem they can build, but for the horizontal thing, they have to have a support structure, right? You have to start building a support structure from the base so that when the horizontal part comes, it will be able to do that. After that, you have to remove the support structure. So this is a waste of time and effort, that is one thing. Second thing is, Particularly if you are going to move this additive manufacturing from macro level to micro level or even nano level, macro level removing additive support structure is difficult, at nano level it is impossible. So you have to come up with a way so that you do proper toolpath planning, so you don't need any support structure at all. So this I click. So that is the motivation of this particular study. Lot of text. I am going to skip all this text. Okay, so look at this. This is the structure I want to make. Obviously, the central piece I don't need any support structure, but all those extended arms and all I need to have a support structure. So how I can do that without that? I have to have a planning. How I am going to do that? We develop some algorithms for that. So that will tell which part should go first. So there are sometimes these algorithms will give you a clear answer, but sometimes there can be a dilemma. For example, everyone knows number 1 is the first one to build, but 2 or 3 I can switch them, right? 3 can become 2, 2 can become 3. So there will be a tie, so your algorithm should come up with some way to decide which one is going to be the next part. But once you decide that, for example, I decide that is going to be my 2, this is going to be my 3, then my 4 has to be next to 3 because I am branching out from them. So these type of logical things, again I repeat, is not the only way of doing it. So whatever I am showing you the problems and what I did is just one way. You can come up with some other way. For example, you can tell I am going to do the 2 and then I will do the 5 because I will finish one side everything, then I will come to the next side. You can think like that. I did not do that because if I do that, then the centroid will get shifted. So my structure can topple, right? So for me the criteria is balancing. So they keep the CG at the middle. So I used this particular approach. There can be many other approach. Okay, so this is just an animation of our logic, basically logic works. That is what it is showing you here. So in CNC language, this is called a dry run. So you can do a dry run to see whether everything is working fine. Then you can do the actual thing. So there are 2 things here. One is that order in which you are building, and second thing is, let us say you build the second part, you want to do the third part, and you should not hit the middle one, right? So you have to have some collision avoidance algorithms, you should think of it. If anybody is interested, you can go look at it. CNC milling, for example, it is a very, very well established research area, a lot of logic, everything is there. But when I say that you do the additive manufacturing, you can change the build axis, that opens up a new door. Lot of challenges will come, lot of work can be done for it. Okay, so now that we will be able to deposit different materials at different locations, that basically is called the graded material. So I can move my anode to whatever location that I want. And if you look at the color changing there, I am symbolically telling that is a different material, right? So I can use this concept, I can build a structure. This is going to have different materials deposited at different locations. This is what exactly is a tailored material. So it is not a naturally occurring material, you are engineering it. So it is a very, very important concept in materials design. If anybody is planning for proposals and all, this is a hard topic. So you can think about it. Now, my ECAM system is capable of doing it. Again, what is the challenge? No one will care about it. It will sit there as an academic exercise in my lab. No one will pay real attention for this. Industry will not even touch it. Why? Because anything they do commercially, they should be able to predict what will happen. Prediction is very, very important. Without that, they won't do. Trial and error is the worst technology. Very, very expensive option. Industries will not like it. So what you really need to move this research to the next stage is design tool that you will be needing. Then only you will be able to take this graded material to a practical view. So if I am able to do this multi-material, these are some demos I am showing you how to make the multi-material. How will they behave, right? If I deposit an aluminum bar, how will it behave? Everybody knows. You have the property, you have FEM software is there, you can make the design, you can do the material property, you can do the simulation, where is the stress, what is the deflection, everything you will be able to do. This is what is important if you want to commercialize anything. There is no such thing available for tailored materials. I am able to deposit different materials at different spot. What is going to be its strength? If I apply some load, what will be its deflection? How do we know that? So that is a problem. So for that we came up with some approach. This is an unpublished work. So if possible, please don't take pictures. My student will be, his thesis depends on this. Okay, he is working on this logic. So basically, he is using a commercial FEM software, but he will do the scripts for that. So he will be adding each and every material, then he will be joining those materials, and then he can make the prediction. That commercial softwares can do. But what is the problem? The problem is aligning, making the geometry. If you are doing a FEM study, you can do the CAD model, then you can do the visualization, those things are fine, but imagine if I have a part that is going to have some 1 million voxel in it, and in this 1 million voxel I am going to have different material at different places. Anyone who has done FEM will understand it's a nightmare. You may need an year to do that, even making your geometry research. So he came with an automated approach. I am showing you here. I believe this video will work. Okay, this is showing you. So he coded everything so that you can make individual voxels and then you can put them together to make a 3D model. So it is opposite thinking. In a normal CAD FEM, you have the CAD model, then you voxelize it. In this case, you go from the bottom. So you can have different arrangements. So this is the FEM results that you are getting. Now, what I want is, I am not going to do this each and every time. So I told him, okay, practically if I have a material, if I have some composition in it, I want to know the strength, what should I do? So then he moved on, he did some simulations and he got a lot of data for different type of configurations, and then he used machine learning for that. So once you have a lot of data, you can train a machine learning model. That model will be able to predict what is it. So if I do some SEM composition and I feed in the composition, it should be able to tell me what is the property. That is the goal. This is to tell that the machine learning works. I'll skip that. And so once he made that prediction tool, the first step I wanted to know is, okay, if it is going to work on a complicated design, to begin with, it should work on a simple design, right? So I told him, okay, let us take a material that is totally aluminum, right? Or it is totally steel. What will happen? So he did that, and this is the Young's modulus he got. If you look at the data book, you will see this is what is the Young's modulus of aluminum. So the algorithm works. So then I gave this tailored material and asked him to predict, and then he also did some experimental testing. He did some tensile testing to see what will be the experimental value. So these are this table is giving you what is the simulated or predicted theoretical predicted value and what is the experimental value he got. So based on that, if you look at the experimental thing, the experimental value is a little bit less than the theoretical prediction. That may be multiple reasons are there. I don't want to do this work here. One possible thing is even your clamping may not be that much accurate. There may be loosening there, or even your position may not be that good in some cases. But now we have a prediction tool that is able to predict pretty well. So the next step, now that we are able to do multiple material deposition, tailored material is possible. We can even predict the property of it. The logical step next is to do the topology optimization. So here I got the inspiration for that from this work. So this is the published work where they are doing the topology optimization. You all know that, right? It's a very structure you have. You do the topology optimization to remove unwanted material, so it should still have the same stiffness but much less of material. That is the idea. So we borrowed that concept and then we tried to have our own logic. So what we did here, if you look at that flow chart, you will see two loops in it, right? So the inner loop will be acting pretty much like the published work where you do the topology optimization. Then I put that into an outer loop. This time what I do is I try to replace material A with material B. Okay, I do this loop. And then I optimize the topology. Once it comes as an optimized thing, then I introduce material C. So this keeps repeating. So this way I should be able to do one step beyond the existing topology optimization. Where if you have a steel structure, you do topology optimization of a steel structure. What I am thinking is, I do the topology optimization not only to minimize the material, but also to replace the material. If there are some places where I can replace material A with material B, that is going to be better. That should be possible. Again, this is an ongoing work. Here to go a long way before I even publish this work, but this is ideal. If anybody is interested to discuss about it after this talk, I will be able to be happy to talk with you. That's all I have for today. Once again, thanks for your time. These are my funding sources. I would like to take any questions.
Thank you, Professor. I think, sir, we can see. Professor, please. Professor Murali, sir.
Yes. Here you. Also, you can see the.
Thank you, Prof, for this wonderful talk.
Any questions? Or else you can meet him later, please. I will be here tomorrow also.
Now I would like to invite the session chair to felicitate our keynote speaker.